water. It's wet and it flows. Warm water rises, we all know that. But have we all seen it happening inside an electric kettle? Warm air rises too. It flows, almost like a liquid. The flow of air is what shapes the weather, always changing, no fixed shape. The world is surrounded by fluid, the atmosphere, and 7/10 of the world is covered by water. Liquid and gas, the fluid states of matter. What makes ice so different from water? What makes a fluid fluid? Sand, not firm, yet not fluid either. But wait. Sand, transformed into an artificial liquid. It's dry, but it's fluid. A piece of wood floats. You can make an artificial liquid from many different things. This one uses tiny plastic beads. The lower part of this box is a closed compartment into which an air hose fits. When it's pumped in, the air will be smoothed out into an even upward flow by a layer of sponge rubber. Now the plastic beads. Start up the air supply and the bed of particles evens out. With a strong airflow, it behaves rather like a boiling liquid. In the chemical industry, solid particles of catalyst are often fluidized just like this. And fresh peas are quick frozen using blasts of freezing cold air. Now the supply is turned off. With no airflow at all, the bed is solid, nothing like a liquid at all. With just a gentle airflow, it changes completely. The particles jostle around constantly. Their movement is what gives the artificial liquid its fluid behavior. All the particles in the bed are moving, so the bed is free to flow, like a liquid. This, in fact, is just how we imagine atoms and molecules in a real liquid, constantly jostling, constantly moving. Imagine water. The atoms and molecules are attracted by electrical forces. To prevent them joining up, though, there's the constant movement. But if the temperature drops, the electrical forces take over. The molecules are snatched into a rigid lattice, the molecular structure of ice. The ice melts. The molecules begin again their random dance. The speed of movement, the average speed, depends only on the temperature. Apply heat and the temperature rises. The movement of the molecules is faster. The water boils. There's enough movement now, enough energy, for some of the molecules to escape. Evaporation. The water becomes a vapor. Even when water is cold, there's some evaporation. Chilly British seas give plenty enough water vapor for all the clouds we ever need. The atmosphere is fluid. This film is speeded up. There may seem to be very little order or pattern in the movement, but that's not always so. We may never have seen a real tornado, but we've all seen something that's very similar. Notice the shape. The flow patterns of water and air are often almost the same. It's something you may notice in many situations. A solid object moves through a thick, viscous liquid. The pattern it leaves builds up slowly. In air, it happens much faster, but there are similarities. Notice the curly shapes and look for something similar in the smoke patterns here. Notice the turbulence in front of the plate too. And compare now. A rounded shape helps to smooth out turbulence at the front. With the shape of an aircraft wing, the turbulent wake at the back almost vanishes too. But how do aircraft fly? What gives wings their lift? In this experiment, the flow of water is marked by bubbles. Because the flows of water and air are so alike, we can use water to watch the action of an aircraft wing. The dark vertical lines moving across the screen show how fast the water is flowing. At the moment, the wing is horizontal, but in flight, an aircraft wing is tilted. Now, the speeds of flow over the wing and under it are different. It's faster over the top. Horizontal, remember, the speeds are the same. Now tilted. Somehow this faster flow over the wing must pull it upwards and give it lift. And you can begin to find out why this happens with a very simple experiment. All you need is a teaspoon. Once in the water, the spoon is pulled strongly and held in the downflow. This isn't enough to explain aircraft flight completely, but it's a clue. Modern jets are as safe as any aircraft in the sky, but the bigger they get, the more they present problems for other aircraft. To show why, this jet has just flown past a tower fitted with smoke generators. Half a minute later, and some distance behind the aircraft, the smoke towers are making the danger dramatically clear. The clock is recording the speed of the vortex. Just imagine the effect of this on another aircraft. problem is caused by the tips of the wings. A model wing in a wind tunnel shows how the vortex starts. Apparently, all wingtips cause these twisters of airflow. They seem to be unavoidable. And the results get more violent the bigger and heavier the aircraft. The smoke experiments have shown exactly how far behind an aircraft the vortex wakes extend and how long they last. And they've led to safer rules for any other aircraft that might be taking off or landing nearby. The surface of a liquid has its own fascination. How useful to be able to walk on water. It's almost as though the liquid has a skin. If you go about it the right way, even metal will float. Soap bubbles are pulled and changed by the forces that operate at the surface of a liquid. A bubble is a thin film of liquid with a great deal of surface, and the pull of surface tension is very real. Surface tension is what pulls a drop of water into its rounded shape, as close to a sphere as the force of gravity will allow. Inside a liquid, the electrical forces pull equally in all directions. But at the surface, the pull can only be sideways and inwards. So, a drop of water is pulled into a sphere. Coffee with milk added. Let's see how this splash compares with our artificial liquid. Was it the same? Notice the drop of liquid forming at the top, nipped off by the pull of surface tension. Does the same thing happen here? Our artificial liquid isn't a perfect model. It doesn't have any surface tension at all. This drop is falling onto a thin film of milk. Surface tension and gravity acting together. Machines that use liquids to transmit power. Forces can be greatly magnified by hydraulic machinery. Muscular force alone can be used to raise a lorry. A model hydraulic press shows the principle. Press down on the right and there's a magnified upward force on the left. For hydraulic machinery, two properties of liquids are vital. One, it's almost impossible to squeeze them into a smaller volume. And two, when you do squeeze them, the molecular movement transfers the pressure evenly in all directions. The larger piston has twice the area of the smaller one. The upward force is doubled. Tunnelling machines use hydraulic motors. To gouge through rock, the cutters must be able to exert really gigantic forces. In this case, the forces are rotary. The action results from an adaptation of the hydraulic press. The motors for these machines are actually very small, not much bigger than a football, in fact. An important point is this. Remember, the motors are driven by liquid. Liquid pumped through flexible pipes. This feature is one of the great advantages of all hydraulic machines. Here's a demonstration. An ordinary domestic electric drill. This is connected to a small pump. The pump drives hydraulic fluid through flexible pipes to a rotary hydraulic motor. Switch on the drill, and the fluid starts pumping, and the hydraulic motor starts turning. And the turning force is big enough to lift the weight of a fully grown adult. And it works even if you tie a knot in the pipes. Every part of this complicated machine is worked by hydraulics. The bucket and the arm mechanism are worked by hydraulic rams. The cab is turned by a rotary hydraulic motor. Notice the flexible pipes. And each of the caterpillar tracks is driven by its own rotary hydraulic motor. Altogether, 6 different movements on this machine are worked by hydraulics. And all the different mechanisms are driven from just one pump unit, seen here at the back of the cab. Hydraulics and flight, 2 major applications of the science of fluids.